Hi, everybody. Hope you guys had a great weekend. So what we need to get done today as it relates to the exam is we need to finish up talking about free radical halogenation. So what we have left for that reaction is to consider what controls or affects radical stability and how we might measure radical stability. And then we need to look at some examples of free radical halogenation. So in lecture on Friday, we introduced this reaction. So remember, it was an alkane plus either Br2 or Cl2 in the presence of heat or light. And we went through this free radical chain mechanism. And we saw in that mechanism that we generated halogen radicals, we generated carbon radicals, and understanding the stability of both the carbon and the halogen radicals helps us understand different aspects of this reaction. So at the beginning of lecture today, what we're going to do is we are going to think about how we're going to measure radical stability and look at various carbons and their substitution and how that affects radical stability. And then we'll talk about the chlorine and bromine radical stabilities for something a little bit later in class today. And I'm hoping we can finish all of the exam material in this 50 minutes. So that then you guys have the rest of the week until Thursday to prepare for your exam. Okay, so let's go ahead and think about radical stabilities. So we're going to say understanding radical stabilities. All right, so we can actually get a direct measure of radical stability by using the bond dissociation enthalpies. Okay, and these bond dissociation enthalpies, which you might have remember the acronym for that is BDE, you use these back in general chemistry to calculate the delta H of reactions. And it turns out that that bond dissociation enthalpy is directly related to the formation of radicals. Okay, so what I want to mention then is, well, what is the bond dissociation enthalpy and how can we use that to understand radical stability? Okay, so the bond dissociation enthalpy and we can abbreviate this as BDE. Okay, and so that actually equals the delta H, or the difference in enthalpy between the reactants and products for the homolytic cleavage of a bond. Okay. So what we can do is if we understand that the delta H is the difference in the heat between the products and the reactants, we can use that information to compare various radicals as compared to their starting materials. So let's think a little bit more about this. So we're going to take some generic bond, so X and Y. X and Y can be any atoms you want them to be. It could be bromine, bromine. It could be carbon, hydrogen. It doesn't matter what those two atoms are. Okay, and so if we consider the homolytic bond cleavage mechanism, remember that both atoms of the bond end up as a radical with a single electron going in each direction. And so in this case, we would end up with an X radical and a Y radical. Okay, so the delta H of this reactance, or of this reaction rather, where we're considering, the difference in energy between reactants and products, that's defined as the bond dissociation enthalpy. Okay, so what we can see here is, in this case, the delta H for the XY bond equals the bond dissociation enthalpy of the XY bond. Okay, and so we know that the various energies of reactants and products are dependent on the stabilities of those two species. So if we were just to look at a plot of delta H as we go through the reaction progress of this homolytic cleavage, so essentially our reaction coordinate diagram, what we would have at the starting material is our XY bond intact, and then at the products we have our X radical and our Y radical. So here I have X radical and Y radical. Okay, and so as we mentioned, as we affect radical stability, that affects the energy, at this position. Okay, and so the difference in energy here, so this is the delta H. Okay, so it's the difference in energy between the reactants and the products, or the products and the reactants. Okay, and so that delta delta H is the bond dissociation enthalpy. So when you go, into these tables and tables of data, which we have available to us, like for example, in our textbook, it's at the very back. So that's where this data is coming from, is by measuring, the heat of this reaction, the homolytic bond cleavage. Okay, and so what we can think about is how does changing both the stability of the XY molecule, whatever it happens to be, and the X radical and the Y radical, how changing those stabilities might affect the delta H. Okay, so let's just hypothetically here for a second, what would happen to energy if the X radical or the Y radical was more stable? Would the energy go up or would the energy go down? Okay, so remember, as we decrease energy, we increase stability. Okay, so maybe if we had this, other process, we, could have this as our reaction coordinate diagram. Okay, and notice how our delta H has gotten smaller. Okay, so as we increase the stability of the X radical and or the Y radical, we decrease the bond dissociation enthalpy. Okay, and so that relationship is how we're going to be able to compare various radical stabilities. Okay, so let's make that statement. Okay, so as X and or Y radical stability increases, its energy goes down, and that makes BDE decrease. Okay, so when we, like in a few minutes, we're going to look at a series of carbon-hydrogen bonds and their bond dissociation enthalpies, and we'll be able to compare the BDEs to get at the radical stability of the various carbon radicals, and then we can make some conclusions about what factors or structural features of the molecule control the radical stability. Okay, and there's one other point that we should make here, and that has to do with the strength of the XY bond. Okay, so let me write out what this trend is and then I'll explain it. Okay, so as the XY bond strength increases, I'm trying to make that look nicer, strength increases, BDE increases. Okay, so if we have a stronger bond that would be more stable, that would lower the energy of XY, that molecule, and that would again increase the bond dissociation enthalpy. Okay, and so what I want you to rationalize at this point is we basically have three ways of kind of asking the same question now. You could be asked to rank bond dissociation enthalpies, based on the molecules and structural features we're about to talk about. You could rank molecules based on the X or Y radical stability, or lastly, you could rank them in terms of bond strength. Okay, so those three things, radical stability, bond dissociation enthalpy, and bond strength, are all related. Okay, and you would go about answering those questions in the same way. Okay, so what I want to do now is look at carbon radicals, because that's going to be important in, circling back to think about our free radical halogenation reaction that we, finished up in class on Friday. All right, so let's consider carbon radicals. So carbon radical stabilities. All right, so what I'm going to do is write out a series of carbon radicals. So we're going to draw the homolytic bond cleavage, and we'll classify them in the same way that we classified carbocations as primary, secondary, or tertiary. We will look up the BDEs, or I'll just give them to you more, actually. And then using those bond dissociation enthalpies, we'll make some conclusions about the stability of the radicals. And we'll see there's a trend between primary, secondary, and tertiary. Okay, so let's go ahead and do that. So first, let's look at a primary formation of a primary radical. Okay, so we're going to homolytically cleave that carbon-hydrogen bond. This is going to give us a primary radical and an H radical. Okay, so it's primary because the carbon that bears the radical is bound to one other carbon. So here we're assuming that the R group cannot be a hydrogen, but is instead a carbon. So this one would be primary. All right, so we can do the same thing for secondary. So I'm going to replace one of those central hydrogens with a carbon. And we would have the same mechanism where we're going to do a homolytic bond cleavage. And now we have a secondary radical because the carbon that bears the radical is bound to two other carbons. And then lastly, we could generate a tertiary radical. So that's where the carbon that we're going to, form the radical at is bound to 3 other carbons. So we have the same homolytic cleavage mechanism that we've had up above. And let's draw the products here. Okay, so we have a carbon radical and we have a hydrogen radical. All right, so let me label these. Okay, secondary and tertiary. I'll go ahead and highlight them too so you can see those. Okay, so notice between these 3 reactions, or these 3 carbon-hydrogen bonds, that the hydrogen radical is similar between them. So the stability of the hydrogen radical isn't going to play any role in affecting the bond dissociation enthalpy. So the differences in BDEs that we see for these 3 homolytic bond cleavages is going to be solely dependent on the stability of the primary versus secondary versus tertiary radical. Okay, so let me give you the bond dissociation enthalpies. Okay, and these are given in kcals per mole. And again, there's a table in the back of our textbook that has, probably hundreds of bonds and their corresponding BDEs. All right, so I went into the table and I looked up these values. And so the formation of a primary carbocation, the BDE is around 101 kcals per mole. Formation of a secondary radical is 99 kcals per mole. And then lastly, for a tertiary radical is 97 kcals per mole. Okay, so remember what we just talked about up above. We said that as we increase radical stability, we decrease BDE. Okay, it's easier to break the bond if the radical is more stable. Okay, so let's make those trend notes over here. So as we go this way, we are increasing radical stability. Okay, and then we could also make a note about bond strength. So as we go up, remember that is inversely related to radical stability. So as we increase BDE, we increase bond strength. And so as we go up, we're increasing bond strength. Okay, so the primary carbon-hydrogen bond is a stronger bond than the secondary. The secondary is stronger than the tertiary. Okay, so now let's go back to radical stability. Okay, so now we've seen that a tertiary radical is more stable than a secondary radical, which is more stable than a primary radical. Is that the same or is that different for carbocation stabilities? Okay, so hopefully you said the same. Okay, and let's think about why that might be. Okay, so think about a carbon radical. Is a carbon radical electron deficient or is it electron rich? So if we count the number of electrons around a carbon radical, we'd get to 7, right? So that's fewer than the 8 that's wanted. So carbon radicals, like carbocations, are electron deficient. Okay, so let's make this note. Okay, so we can say up above that R groups, or another way to say that is increasing substitution, increase carbon radical stability, just like carbocations. So let's make a note about that. Okay, so radicals are electron deficient like carbocations and are stabilized by neighboring sigma bonds. Okay, and so let's think about what that is, right? So what did we just describe? Where the carbon radical is stabilized by adjacent carbon hydrogen or carbon-carbon sigma bonds. Okay, so we just described hyperconjugation. Okay, so I want to go ahead and just look at a picture of that really quick because it might not be clear how hyperconjugation can operate here. Like we haven't actually talked about, what is the hybridization of a carbon radical. Okay, so the hybridization of a carbon radical is sp2, and that single electron, the radical, resides in the p orbital. So we have a p orbital with a single electron in it. Okay, so let's go ahead and just draw a generic radical and consider, how this is much like hyperconjugation. Okay, so the left-hand carbon, I'm going to place the radical, and the right-hand carbon is a methyl group. Okay, so I'm basically drawing a primary radical here. So we have our p orbital, and we can put our radical, we'll just indicate that it's there, but remember that that electron density is spread out over both lobes of the p orbital. Okay, and so we depicted hyperconjugation, something like that. Okay, so where we have electron density going from the adjacent sigma bond that is aligned to the p orbital, and it is stabilizing that electron deficient carbon. Okay, so one other thing I want to notice here is carbon radicals, or actually I'm going to do it on this diagram here. Okay, so this carbon is sp2. Okay, and then we can just make a note, single electron in p orbital. Okay, that's what we've drawn there. All right, so now we know that basically hyperconjugation stabilizes radicals just like carbocations. So we have one tool that allows us to rank radical stabilities. Okay, and then the other one, we're going to talk about two other ones that are also the same as carbocations. So let's talk about resonance, and then we'll also talk about inductive effect. Okay, so let's do our next point. So our next point is resonance stabilizes radicals. And then we'll just make a note, what are we looking for here? So we're looking for delocalization of electron density through the pi system. All right, so what we're going to do for this is we'll look at allylic and benzylic radicals. Those are the same radicals, or the same positions that we talked about, carbocations and their stability through resonance. Okay, so let's go ahead and compare this radical to this radical. Okay, so how could I compare these two radical stabilities? Well, one is I would need the BDEs for the corresponding carbon-hydrogen bonds that would make that radical. Okay, so we could look up the value of the bond association enthalpy for a primary carbon-hydrogen bond, and that's something like 101 kcals per mole. Okay, then I'll go into the table at the back of the textbook and look it up for an allylic carbon-hydrogen bond, and we would see it to be 89 kcals per mole. So that's significantly less. And in fact, it's less than a tertiary radical that we talked about, up above. Okay, so resonance plays a huge role in stabilizing these radicals. Okay, so that's all fine. We can recognize that when the radical is adjacent to a pi system, so this is the allylic position, that it's able to participate in resonance, but we've actually never seen resonance on radicals. Like, how do I actually draw resonance structures where I'm only moving a single electron at a time? Okay, so let's go ahead and do that down below. Okay, so the allylic radical is stabilized by resonance. Okay, so allylic radical is stabilized through resonance. And let's draw that down below. Okay, so here was the radical we started with. All right, so let me show you how this looks. Okay, so we're gonna have the radical combining with one of the pi electrons. Okay, so now I'm gonna separate the two electrons in the pi bond. I'm gonna have one combine with the radical electron, and then I'm gonna have the other go to the other carbon of the carbon-carbon pi bond. Okay, and so let's think about the structure then that results. Okay, so these two arrows together are gonna move the position of the pi bond, and this last arrow on the left is gonna move the position of the radical. Okay, we're showing us where the radical is going. Okay, so the resonance structure that we're gonna see here is this one. So we've moved the position of the pi bond and the radical. They basically have changed places, right? And so we can see that there's two carbons now that are bearing the burden of being electron deficient, or only having 7 electrons around them. Okay, so the last one I want to look at is a benzylic radical. Okay, so we can just make a note about that. So benzylic radicals also stabilize through resonance. Through resonance. Okay, so let's take a look at that. So the first thing we could do is consider the bond association enthalpy, or the BDE, to give us a benzylic radical. So that would be something like this carbon-hydrogen bond. Okay, so the BDE equals 90 kcals per mole. Okay, so that's around the same as the allylic position, and I realized I didn't label these as BDE, so I'm gonna go up there and add that. So if you're looking at the notes later without me talking, you'll know that those are the values I was giving. Okay, so a primary and benzylic radical is roughly the same stability as a primary and allylic radical. Okay, and so what you could rationalize then is that, through homolytic bond cleavage, you arrive at this benzylic radical. And I'll just draw one resonance structure, but you could, spend some time practicing drawing resonance structures of radicals to draw the other. Okay, so we can have the single electron combined with the adjacent pi bond, and then that other electron goes to the carbon to move the position of the radical. And so one of the resonance structures you could get to is this one. Okay, but then I'll just say, etc. You could draw some more resonance structures there. Okay, so allylic positions and benzylic positions stabilize radicals through the adjacent pi bonds, okay, and that's through resonance. Okay, so the last thing that we get to talk about that controls radical stability is the inductive effect. Okay, so let's talk about the inductive effect and radicals. Okay, so inductive effect and radical stability. Okay, so what we have to think about then is, well, what did electronegative atoms do to carbocations, which were electron deficient? So remember, electronegative atoms stole electrons from the already electron deficient carbocation and destabilized them. The same holds true here. So a radical, being near an electronegative atom would be less stable than if that electronegative atom was absent. And that's because the electronegative atom is stealing electron density through the sigma bonds, destabilizing the already electron deficient radical. So let's just look at one example of that. So let's just imagine we had this, trifluoro methyl substituted radical, and we're going to compare it to just some other generic secondary radical. Okay, so I don't actually have the BDEs here, but let's just make a note that these fluorines are stealing electrons from that already electron deficient radical, so this would be a less stable radical. And this would be the more stable radical. So if we could look up the BDEs, which one of these molecules, the molecule on the left or the molecule on the right, would you expect to have a lower BDE? Okay, so hopefully you said that the lower BDE will be the one that's the more stable radical. So this one would have a lower bond association enthalpy. This one would have a higher bond association enthalpy. Okay, so now we have, something to gauge radical stability. So now what we need to do is go back to the reaction we were considering, which was free radical halogenation of an alkane, and consider how we can use this information to think about the regioselectivity, so which carbon-hydrogen bond we react with in the formation of the products. Okay, so I'm going to pause here for a second, and I'll come back and we'll revisit that reaction. All right, everyone. I'm back here to talk about free radical halogenation. So what we're going to do is use the information we just learned about the relationship between bond association enthalpy and radical stability, and more generally our knowledge of radical stability, to understand various aspects of free radical halogenation, of which we talked about the mechanism on Friday. So you might want to pause here and go revisit that mechanism just to make sure that you can understand, the various aspects I'm about to talk about. Okay, so in that mechanism, and here we're only considering the propagation steps, because that's really the heart of the reaction. That's where most of the reagents and reactants are being consumed. And so in those propagation steps, we saw basically two different radicals. We saw the halogen radical, and that halogen radical abstracted a hydrogen from carbon to generate a carbon radical. Okay, and so both the stability of the halogen radical and the stability of the carbon radical that is formed plays a role in determining various aspects of the reaction. Okay, so what I want to do first is look at an example. All right, and this example we're going to look at is this one. Okay, so we're going to take this 2-methylpropane and we're going to react it with X2, and I'm not going to clarify at this point whether it's bromine or chlorine, because we're actually going to compare them. And we are going to use light here. You could use heat or light, remember. Okay, and what I want you to first rationalize is, well, how many different products could form? Okay, so previously we just looked at methane, CH4. There was only one type of hydrogen that would give us the one product, which was CH3X, whatever X was, bromine or chlorine. Okay, so in this case, notice how I have these 3 methyl groups. So the first thing we should ask is, are those 3 methyl groups equivalent or not? Okay, well, they are equivalent. They're all attached to the same sp3 hybridized carbon. And then we also have this single hydrogen here at the tertiary position. Okay, so those 3 positions, or those 2 positions, the 3 methyl groups, all those 9 hydrogens, and then the 1 tertiary position that we saw, those are the 2 possible products that we could arrive at. All right, so let me try to draw those 2 products. Okay, and it doesn't matter for the primary positions what methyl group you, take the hydrogen from. So I just chose to put it on that N carbon arbitrarily, but again, you could have put it on, for some reason this isn't letting me unselect. Okay, let's try that again. Okay, so I decided to put it on this N carbon, this carbon over here, but you could have put it on this carbon or this carbon. All right, so that's one potential product. The other potential product is if I were to replace that tertiary hydrogen with our halogen. Okay, so these are our two possible products. Okay, so first, how would you relate these two molecules? How are they related? Are they stereoisomers or are they some other type of isomer? Okay, well, hopefully you realize they have different atom connectivity, so they would be structural isomers. Okay, and we could even call them then regioisomers. Regioisomers. Okay, and so whether we form one of these products in preference to the other would dictate whether or not this is a regioselective reaction. Okay, and so what I want to do is give you the experimental yield. So when we actually went and ran this reaction in the lab, the experimental yield of both of these structural isomers for when we used chlorine and for when we used bromine. Okay, and I'll also introduce something called the statistical yield. Okay, so I'll leave a line here for the statistical yield, but I'll fill that out last. Okay, so we'll have the statistical yield, and then we'll have the experimental yield. And we'll do that for X equals chlorine, and then X equals bromine. Okay, so when X equals chlorine, we get 62% of the primary halide and 38% of the tertiary halide. If I were to change the halogen to bromine, then I completely change the selectivity of this reaction. I get 0% essentially of the primary halide and roughly 100% of the tertiary halide. Okay, that's a huge difference in selectivity, right? Okay, so before we move on, because this is going to be a huge question we're going to have to address, like why do I get this different distributions of structural isomers? Like in other words, why is there different regioselectivities between these two reactions? So before that, I want to introduce a term called the statistical yield. Okay, so the statistical yield assumes that all of the hydrogens within a molecule react at the same rate, meaning it would take the same energy and it would, we'd have the same activation energy for abstraction of a primary hydrogen versus a tertiary hydrogen. But we know that's not true, right? Because we learned about radical stabilities. All right, so how could we figure out the statistical yield? Well, first, what we would have to do is figure out how many hydrogens would give each of the products. Okay, so we kind of already talked about this, but we have these 3 hydrogens at this carbon, and then I have 3 hydrogens at that carbon and 3 hydrogens at that carbon. All 3 of those primary positions would give me that same product. Okay, so I have 9 primary hydrogens, and I just have the 1 tertiary hydrogen. Okay, so the statistical yield is taken by taking the number of hydrogens that would give that product and dividing it by the total number of hydrogens. Okay, so what would you then say the statistical yield for the primary halide would be? So if we assume that all 10 hydrogens react at the same rate, 9 of those 10 would give me the product shown, we would get a statistical yield of 90% for the primary halide. And then only 1 of those hydrogens gives me that tertiary product, so 1 into 10 gives me the 10%. Okay, and again, this assumes, assumes all 10 hydrogens, so this was 10 total H's, so all 10 H's react at the same rate. Okay, so comparing the statistical yield to the experimental yield for chlorine and bromine gives us some insight into the reaction and what's governing the selectivity. So first, if we were just to compare the statistical yield to when X equals chlorine, we could see that, if I was just to compare these two numbers, 10% to 38%, I'm getting more of the tertiary product than I would otherwise expect. Okay, and so really where that comes from is, well, we know there's difference in the stabilities of the radicals as intermediates that we'd go through in this mechanism. So the stability of the radicals at the various positions, so in this case primary or tertiary, is going to help dictate the regioselectivity. Okay, so let's just make a note about what we're observing between chlorine and bromine. Okay, so using some of the terms we used before, we could classify halogenation when X is chlorine versus X is bromine as either regioselective or not. Okay, so since bromine, when X is bromine, gives us exclusively the tertiary halide, we would say that it's regioselective. It turns out that chlorination is not very selective at all, and we usually get some of all possible structural or regioisomers. Okay, so let's go ahead and make those notes, and then we'll try to understand why that is. Why is one of these reactions, giving us a different regioselectivity than the other when mechanistically they're similar? Okay, so here's what we observed. So chlorination is not regioselective. Okay, and we can see this because we would obtain some of all possible regioisomers. Okay, so the regioisomers, are not formed in preference to the other, so it's not regioselective. Okay, on the other hand, bromination, okay, when X equals bromine, is regioselective. Okay, and it's regioselective to go through the most stable radical. To go through the most stable radical. And we're talking about the carbon radical here. So essentially in bromination, when we do that, when we form the bromine radical in the first or when we form the bromine radical in the initiation step, in the first propagation step, that bromine radical is going to remove a hydrogen in such a way to form the most stable carbon radical possible. For the chlorine radical, it can remove any of the hydrogens really. Okay, and how we can understand that selectivity is by thinking about the stabilities of the bromine versus the chlorine radical. Okay, and there's a really long section in our book here, and it talks about, you calculate the various delta H's of reactions and compare them as endothermic or exothermic, and then you use something called the Hammond's postulate to compare. We're kind of going to streamline that and just cut to the chase. What is the most important thing to help us understand this selectivity? Okay, so the last thing that we need to do here is figure out this difference in selectivity. Okay, so understanding selectivity difference. Okay, so the question that we're asking is, why is bromination regioselective and chlorination not regioselective? Okay, and the way we're going to do this is by comparing the bromine radical to the chlorine radical. Okay, so if we think about the mechanism otherwise, bromination and chlorination are, parallel. So I go through the same intermediates in bromination as I do chlorination, with the exception of the halogen that bears the radical, forming after the initiation step. The carbon radicals would be the same between bromination and chlorination. Okay, so the selectivity difference must have to do with, some difference in stability of bromine versus chlorine. Okay, so, what would I go and look at to figure out what the, difference in stability for the bromine versus the chlorine radicals are? Well, I would look at the bond association enthalpies of the bromine versus the chlorine bond. Okay, so the BDE of that bond equals 46 kcals per mole. The BDE of this bond is 59 kcals per mole. Okay, so now that we have the BDEs, we can start to think about the radical selectivity. Okay, so given that bromine has a lower BDE, is the bromine radical more or less stable than the chlorine radical? Hopefully you said that the bromine radical is more stable. Okay, and over here we'll make a note that the chlorine radical is less stable. Okay, so the bromine radical is more stable and the chlorine radical is less stable. Okay, so now let's try to think about that in terms of energy. So the bromine radical is more stable, therefore it's lower in energy. And then the chlorine radical, which is less stable, is higher in energy. Okay, so let's think about what that has, what that stability and relative energies between the bromine and the chlorine radical, what does that have to do with selectivity? Well, think about what's happening. So either the bromine radical or the chlorine radical is abstracting a hydrogen. So the radical that is less stable and higher in energy, it has more energy, more potential energy to remove one of the hydrogens. And so when we have the chlorine radical, since it's so high energy, it doesn't really have a preference for which hydrogen it abstracts from carbon. Okay, and so what we would say is, since it's higher in energy, it's more reactive. And since it's more reactive, it's less selective. Okay, because since it's at a higher energy, it has enough energy to then, abstract any one of the various carbon-hydrogen bonds within our alkane starting material. Whereas the bromine radical, that is lower energy, it's less reactive. Okay, so it really only has enough energy to abstract the hydrogen that gives me the most stable carbon radical. So it ends up being selective to go through that most stable carbon radical. Okay, so since it's less reactive, it's more selective. Okay, so what we can see then is that since the bromine radical is more stable and lower in energy, it's less reactive and more selective. Okay, so we can use a little bit about the bromine versus the chlorine radicals to understand that selectivity. But what does this mean for you guys? As you're predicting products and thinking about these reactions, mechanistically, these two reactions are no different, right? But there is this difference in energy between, the bromine radical and the chlorine radical, which accounts for the selectivity difference. But what you need to be able to do is predict the products of these reactions. Okay, so for a bromination reaction, you would think about what's the most stable carbon radical that would form, and that's going to give you your product. Whereas if you're going to do a chlorination, you would get sum of all possible products. Okay, so the last thing I want to do here is just do that. Let's compare the same starting material with chlorination versus bromination, and then we'll look at one last example, which will highlight stereochemistry. Okay, and after we looked at these three examples, that will be the end of exam material. And so I probably won't post anything additional on Wednesday, but I will send a Canvas announcement out about office hours and thinking about how I can answer questions as you guys have your exam coming up on Thursday. Okay, so let's first look at this substituted benzene, and we'll do bromination first. Okay, so I'm going to make that more clear. It just looks like a random wavy line. Let's count the carbons, and again, I'm just doing that so we can talk about it. So if you're considering positions 1, 2, or 3, which position would the radical be the most stable? Okay, so at position 1, 2, or 3. So at position 3, it would be primary. At position 2, it would be secondary. And position 1, it'd be secondary and benzylic. Okay, so hopefully you thought about that secondary and benzylic position as being the most stable. Okay, and what else did we learn about radicals, which is going to help us think about the stereochemistry? Okay, so remember that carbon that bears the radical is sp2. Therefore, it's trigonal planar. Right, so what did we learn as it relates to carbocations that were also trigonal planar and sp2 hybridized when the next reactive reagent approaches that radical or carbocation, it can do so from either side. So whether it's a nucleophile attacking a carbocation, it can do so from either face. And in this case, when another molecule of Br2 approaches that carbon radical, it can approach from either face. And so we end up getting a racemic mixture. Okay, so the products of this reaction would be the racemic mixture at the benzylic position, coming from the secondary and benzylic radical. Okay, so this is racemic. Okay, and again, in terms of stereochem, since that this radical intermediate that we have right here is sp2 hybridized and trigonal planar. When the bromine Br2 approaches that radical, it can do so from either face, and then we'll get that mixture of stereoisomers. All right, so let's take that same exact starting material and do chlorination. Okay, so when we're predicting the products for chlorination, we essentially get sum of all possible regioisomers. Okay, and so we're still not reacting, we're only reacting the sp3 hybridized carbons in this reaction. It was halogenation of an alkane, an sp3 hybridized carbon. So we're not going to touch any of the benzenes or any of the carbons of benzene, any of the carbon hydrogen bonds of benzene. Okay, so we still can only chlorinate at carbons 1, 2, or 3. So we have 3 possible regioisomers, and within some of those we'll have also some stereoisomers to consider. Okay, so if we chlorinated at position 1, we would get a racemic mixture at that position. Okay, so if we wanted to draw all products including stereochem, this is what we would arrive at. Okay, so we have the racemic mixture at carbon 1. What about at carbon 2? Does that constitute a chiral center? It does, so we'd have the racemic mixture at carbon 2. And then lastly, we would have halogenation or chlorination rather at carbon 1. Okay, and now, or at carbon 3 rather, and that doesn't constitute a chiral center, and so we don't need to show the stereochem there. I'm just gonna go ahead and add my carbon number labels on here so you can track what was happening. Okay, so again, we get sum of all possible regioisomers with chlorination because it's not a regioselective reaction due to the instability of the chlorine radical. All right, and one last example to talk about something related to stereochem. Let's look at this. Okay, so I'm going to look at this molecule and I want to do bromination. Okay, so remember we can use heat or light to initiate this reaction. Okay, so first, looking at this molecule, we have 5 carbons in our longest carbon chain, but we also have these methyl groups off of carbon 2 and the methyl group off of carbon 3. Okay, so the first thing we want to consider is which position would we form the radical? Okay, so looking at carbon 2, I want you to realize there is no hydrogen at carbon 2, so I cannot form the radical there. I cannot abstract a hydrogen when a hydrogen doesn't exist. So we are looking at carbon 3 as being, the most substituted carbon that bears a hydrogen, so I can form the radical at that position. Okay, so what I want to think about is what happens to the stereochemistry of that methyl group when I form the radical at carbon 3. Okay, so remember that the radical is sp2 hybridized and trigonal planar. So that radical that we've just drawn has no memory of the stereochemistry of the methyl group in the starting material. All right, so when we move forward to predict the products, we're going to end up with a racemic mixture because we went through this achiral intermediate where we could add bromine to either face. Okay, so bromine could come in from the top face to give us that stereoisomer, or bromine could come in from the back face to give us this stereoisomer. Okay, so even though we had a chiral starting material with that stereocenter at carbon 3, when we do the hydrogen atom abstraction to get to the carbon radical, we ablate or destroy the stereochemistry and we end up with this achiral radical intermediate, so that when we continue the mechanism to the products, we end up with a racemic mixture. Okay, so at this point, this is all that we need to cover for our exam material. And so, as I mentioned, I'll send a Canvas announcement out as it relates to how to get questions and how office hours are gonna maybe be a little bit different this week in terms of how I'm gonna run those. And so I'll be looking for an announcement about that. And so I will probably not post another formal lecture then until after next weekend, after our exam has passed, wherein we have 2 more reactions in chapter 8 and we'll start chapter 9. Okay, so again, if you have any questions, there's discussion boards for each of the day's lectures. You can email me, you can Canvas message me. There's a Facebook group where the TAs are quite responsive about answering questions. And then I'll have office hours this week as well, so wherein you can ask any questions about the exam material. Okay. All right, well, I will talk to you guys all maybe at office hours, but if not, I will be talking to you guys at lecture next Monday.